Some of history's greatest landmarks should have crumbled into dust long ago. We are about to uncover 30 forgotten tools that built these impossible structures, revealing an ingenuity that rivals our own. This journey will give you a completely new understanding of ancient engineering, one that challenges everything you thought you knew about the past. How did civilizations without modern technology achieve such perfection, and why were their methods lost to time? The answers lie not in magic, but in instruments of stunning simplicity and brilliance. What does it truly mean to build something that lasts for millennia? A single right angle, repeated thousands of times, can build an empire. This is the fundamental truth behind the Groma, a tool so simple its genius is almost invisible. Picture a long wooden staff, and at its top, a cross shaped like a plus sign. From the ends of each arm, heavy plumb bobs hang on strings, pulled straight down by gravity. To use it, a Roman surveyor would plant the staff firmly in the ground. He would then sight along one pair of opposing plumb lines to establish a perfectly straight first line. Then he would pivot and sight along the other pair, creating a second line at an exact 90-degree angle to the first. This was the magic, the creation of perfect geometry in a wild and untamed landscape. With this humble device, the Romans did not just build roads, they imposed a grid of absolute order upon the world. Their legendary straight highways, stretching for thousands of miles, all began with the alignment of a Groma. The colossal aqueducts that brought fresh water to cities, engineering marvels that required gradients precise to within a fraction of an inch over many miles, relied on the Groma's unwavering lines for their initial layout. Even the foundational plans of entire cities, with their neat, rectangular city blocks and forum squares, were plotted using this instrument. The very foundation stones of the Colosseum itself were set according to the perfect right angles established by the Groma. It provided the invisible skeleton upon which all the marble and mortar were hung. This was not just construction, it was a declaration. The Groma was the physical manifestation of Roman logic and control, a tool that turned chaotic nature into a disciplined, lasting empire. And yet, for all its power, it was just the beginning. An even more ancient device would allow builders to move the very mountains that the Groma so neatly organized. But that rigid geometry was only the first step. Once the lines were drawn, the real work began, moving mountains of stone into the sky. The Roman Volute crane was the titan that answered this call, a wooden giant whose groans and creaks were the sound of an empire rising. At its heart was a simple, brutal source of power: men walking. Not walking on the ground, but inside a massive wooden treadmill wheel. Several laborers would step endlessly forward, like hamsters in a wheel, their collective weight and momentum turning the central axle. This axle was connected to a capstan, a rotating drum that acted like a giant winch, gathering thick ropes wound through a sophisticated system of pulleys. This arrangement created an immense mechanical advantage, meaning the slow, plodding steps of a few men could be transformed into enough force to hoist a multi-ton block of travertine stone high into the air. This was not mere strength, it was strength multiplied by intelligence. With this machine, the Romans built the impossible. The immense, perfectly shaped stones of the Colosseum were lifted and set with a precision that still baffles engineers. The Pantheon's majestic dome, a perfect hemisphere of concrete that seemed to defy gravity, required its components to be raised to dizzying heights, a task for which the Volute crane was essential. The mythology here is not of gods but of human collaboration. It was the synchronized effort of the team inside the treadmill, the shouted commands of the foreman, and the careful hands of the stone setters that turned a vision into an enduring landmark. The crane's design was so perfectly balanced, so effective in its application of force, that its basic principles saw no need for improvement for over 1,000 years. It stands as a testament to the fact that raw power, when channeled through brilliant engineering, can create legends that stand for millennia. Yet, even after these colossal stones were lifted into place, the work was far from over. They now needed to be shaped and joined with a perfection that would make them inseparable for ages. Yet that assembly of stone giants would have been impossible if each block had not been shaped first with impossible precision. The Egyptian copper saw is a tool that defies modern expectations, a blade that was not sharp at all. Imagine a long, flat strip of soft copper, a metal too malleable to cut hard granite on its own. Its true cutting edge was not metal but earth. Workers would create a slurry of water and quartz sand, a substance far harder than the stone they needed to shape. As they pulled the copper saw back and forth, the abrasive sand particles embedded themselves in the soft metal, turning the blade into a moving sheet of countless microscopic teeth. This was not a swift cut, but a slow, deliberate grinding. A single granite block could take a team of workers weeks or even months to saw through, a testament to a level of patience that is almost mythical to our modern sensibilities. This process was not brute force, it was a profound application of material science. They understood that the tool itself did not need to be hard, it only needed to carry a harder substance. The evidence of this quiet genius is locked in the stones themselves. In the depths of the Valley of the Kings, where pharaohs were laid to rest for eternity, granite sarcophagi were crafted with joints so perfect that not even a razor blade can be inserted between them. This flawless fit, achieved thousands of years ago, is the direct result of the persistent, grinding work of the copper saw and its sandy grit. It speaks to a civilization that valued permanence above speed and understood that true power lies not in a single explosive effort, but in the unwavering application of a simple, brilliant principle. But once these perfectly fitted stones were ready, a new, even greater challenge emerged: how to move them across vast distances without machines. That battle against the river was a daily reality in Mesopotamia, where survival itself depended on controlling the water. The true hero of this struggle was not a king or a warrior, but a massive, reinforced plow, an earth-moving machine pulled by teams of oxen. This was not the simple plow used to till a field for seeds. This was a levee builder's plow, a heavy-duty implement built with one purpose: to sculpt the land itself. Its deep, curved blade was designed not to simply scratch the surface, but to dig, lift, and turn over enormous volumes of soil. With a driver guiding the oxen and workers managing the blade, this tool could carve out irrigation canals with astonishing efficiency. More importantly, it could pile the excavated earth into high, continuous banks along the river's edge, creating the vital levees that held back the destructive, unpredictable floods of the Tigris and Euphrates. This was humanity's first great act of territorial defense, a declaration that they would not be at the mercy of nature. By taming the rivers, they created the stable agricultural surplus that allowed the world's first great cities like Ur and Babylon to rise from the mud. The grand ziggurats that pierced the sky and the formidable walls that protected these urban centers could never have been built on land that was flooded every season. Their very existence is a direct result of the hydrological order imposed by the levee builder's plow. This tool represents a profound shift in our story, from shaping stone to shaping the earth itself. It reminds us that the most important foundation for any landmark is not the stone you see, but the ground you cannot see, the ground made stable by forgotten ingenuity. This principle of mastering the earth would be taken to even greater extremes by another civilization, one that needed to move mountains before it could even begin to build upon them. Yet that mastery of the earth and stone would have meant little without an equally profound control over form and proportion. Hidden within the flowing robes of a marble goddess and the flawless curves of a temple column lies the secret of the bronze caliper. This was not a crude ruler, but an elegant, adjustable instrument with two curved legs joined at a pivot. A sculptor would carefully set the distance between the caliper's points on a small-scale model, a prototype for the final, monumental work. That exact measurement could then be locked in and transferred directly onto a weighting block of marble or bronze. This simple act of replication was revolutionary. It allowed for the creation of perfect symmetry in a statue's face, the identical taper along a row of columns, and the harmonious repetition of intricate patterns across a long frieze. The legendary perfection of the Parthenon sculptures, where every muscle and fold of cloth feels alive, was not born from random genius alone. It was achieved through the disciplined, repeated application of this precise tool. The caliper ensured that the vision of harmony and balance, so central to Greek and Roman ideals, was not lost when scaling up from a handheld model to a building-sized masterpiece. This is why these classical works have survived earthquakes and wars for over 2,000 years. Their strength lies not just in the quality of the stone, but in the perfect distribution of weight and stress that only such precise craftsmanship can achieve. The bronze caliper translated an abstract philosophy of beauty into a physical, measurable reality, stone by perfect stone. And if this tool could measure the proportions of a human form with such accuracy, it begs the question, what instruments did they use to measure the cosmos itself, to align their greatest monuments with the sun and stars? But the perfection of a statue or a single building was only a fragment of a much grander design. For ancient civilizations, the ultimate goal was to align their greatest works with the cosmos itself. Long before the intricate gears of the Antikythera mechanism, Egyptian priests employed tools of breathtaking simplicity to achieve this celestial harmony. The most fundamental was the gnomon, a simple vertical rod planted in the ground. By meticulously tracking the length and direction of its shadow throughout the day and across the seasons, these astronomer priests could map the sun's path with astonishing accuracy. They could pinpoint the solstices, the longest and shortest days of the year, and the equinoxes when day and night are of equal length. This knowledge was not merely academic, it was the foundation of sacred architecture. The Great Pyramid of Giza, one of the most accurately aligned structures ever built, faces true north with a deviation of just a fraction of a degree. This was not an accident. It was achieved using another tool, the merkit. This instrument was a narrow, notched palm rib with a plumb line hanging from it. By sighting through the notch and aligning the plumb line with specific stars, priests could establish a perfect meridian line, a north-south axis drawn across the heavens. Imagine the process: a priest on a clear, cold night, patiently waiting for a star to cross his sight line, marking its path on the ground to create a line of absolute direction that would guide the placement of million-ton blocks of stone. This was engineering in service of mythology. A temple aligned to the rising sun on the winter solstice was not just a building, it was a machine for capturing a divine moment, a bridge between the human world and the eternal cycles of the gods. This sacred alignment may be the most overlooked reason for these landmarks' enduring power. They are not just physically anchored to the earth, they are spiritually and astronomically anchored to the universe, a connection that has helped them stand for millennia. If such simple tools could achieve such cosmic precision, what other mundane instruments held the keys to unlocking other profound mysteries of the ancient world? Those alignments with the cosmos were fixed points in a grand design, but the materials to build that design still had to conquer the Earth's most brutal terrain. High in the Andes, the Inca faced an engineering nightmare, moving multi-ton stone blocks up near vertical mountainsides without the wheel, without iron, and without beasts of burden like oxen or horses. Their solution was as brilliant as it was temporary, an extensive network of ramps constructed from compacted earth and meticulously reinforced with heavy mats woven from llama hides. This was not a permanent road, but a disposable highway. Teams of workers would lay these durable, fibrous mats over the packed earth, creating a surface with immense grip that prevented the massive stone blocks from sliding backward under their own weight. Imagine hundreds of laborers, coordinated by rhythmic chants, hauling a single granite block up these improvised slopes. They used ropes made from llama leather and levers made from the toughest wood, inching the stone upward with a combination of sheer human force and clever physics. The mythology here is not of gods bestowing power, but of an entire community moving as one. Once a stone reached its destination and was fitted into place with that famous, jaw-dropping precision, the ramp was dismantled. The earth was scattered, the invaluable llama hide mats were reused or repurposed, and the mountain was left seemingly untouched, with the citadel of Machu Picchu appearing to grow directly from the bedrock. This method reveals a philosophy completely different from the Romans' permanent imposition of order. The Inca mastered the art of temporary engineering, building for eternity by leaving no trace of the construction process itself. Their landmarks stand as mysteries precisely because their most ingenious tools were designed to vanish. This concept of building without a permanent footprint leads us to another civilization that solved a similar problem in a completely different way, one that involved mastering the very thing that should have destroyed their work, water. Yet this vertical ambition, reaching for the heavens from the mountains of Peru, found its ultimate expression in the soaring stone forests of medieval Europe. The medieval French treadwheel crane was a direct evolution of the Roman genius, but scaled up for a new kind of mythic goal, the Gothic cathedral. Imagine a colossal wooden wheel, taller than a man, built right into the skeletal framework of the rising cathedral itself. Inside this wheel, several laborers would walk, step after endless step, their collective weight turning the axle like a massive gear. This was not a hidden mechanism, it was a public spectacle, a visible engine of faith. The groans of the wood and the rhythmic steps of the men inside were the heartbeat of the construction site, powering a winch that hoisted precisely cut stones hundreds of feet into the thin air. The iconic silhouettes of Notre Dame de Paris and Chartres Cathedral, with their impossibly high vaults and delicate spires, are monuments to the power of this machine. It was the treadwheel crane that made the Gothic Revolution possible. This architectural style relied on a delicate balance, where the weight of the roof was channeled outward through flying buttresses. Placing these massive stone supports required a crane that could lift and hold them in a precise position until the mortar set. The entire structure was a high-wire act of physics, and the treadwheel crane was the steady hand that made it happen. The mythology here is palpable. The sight of these wooden giants against the sky, with men walking in a perpetual circle to lift stone toward God, was a powerful symbol of a community's collective devotion. The endurance of these cathedrals is a testament not just to the strength of the limestone, but to the unwavering human spirit that literally climbed inside a wheel to lift it. But such ambition demanded more than just lifting power. It required a tool that could shape stone with the precision of a jeweler, carving the very prayers into the walls. The stone bow drill turned granite into lace. This ancient Indian tool was a masterpiece of controlled motion, a far cry from the brute force of hammers and chisels. Its design was elegantly simple, a small bow like that used for archery, with its string wrapped not around an arrow but around a vertical drill shaft. An artisan would hold a wooden cap on top of the shaft with one hand, applying gentle downward pressure. With the other hand, he would move the bow back and forth. This action spun the drill bit, tipped with a harder abrasive like diamond dust, in a smooth, continuous rotation. The result was not a violent chipping away, but a patient, precise grinding. This controlled rotation was the key to the impossible. It allowed craftsmen to carve delicate perforations through solid marble, creating intricate stone screens so fine they seemed to flutter in the wind. On the towering walls of temples like Khajuraho and the cave complexes of Ellora, this tool was used to sculpt the flowing hair of deities, the delicate petals of lotus flowers, and the complex folds of divine garments with the precision of a modern dental drill. Each push and pull of the bow was an act of immense patience and spiritual focus, a physical prayer etched into stone. The mythology is not in the tool itself, but in the devotion it channeled. The endurance of this art for over 1,000 years is a testament to that sacred patience, a level of care we can scarcely comprehend today. After witnessing such delicate artistry, the mind naturally turns to its opposite, the tools required not for fine detail, but for moving entire landscapes. That delicate artistry of the stone bow drill required a foundation of raw industrial power. While sculptors carved prayers into marble, entire mountains needed to be broken down. In ancient China, this power did not come from armies of laborers, but from the rivers themselves. The Chinese trip hammer, a simple yet revolutionary machine, transformed the very concept of construction. Picture a massive water wheel turned by the relentless flow of a river. This wheel was connected to a series of wooden cams, which acted like a row of mechanical fingers. As the wheel turned, each cam would lift a heavy, pivoting hammer made of wood and iron. At the peak of the lift, the cam would release, and the hammer would drop with crushing force onto whatever lay in the stone trough below. This was not a tool for one person, it was a factory. One water wheel could power an entire battery of these hammers, working day and night without rest. Their primary task in construction was to pulverize. They smashed limestone into a fine powder to be mixed into the mortar that would bind the bricks of the Great Wall. They crushed clay and other materials to create the sturdy earthen cores that formed the foundation of grand pagodas. They could even break large boulders down into smaller, more manageable stones. This was early industrialization, a system that multiplied human effort 1,000-fold. The mythology here is profound. It is the story of harnessing one natural force, the river, to build monuments that would defy other natural forces, like invading armies and the relentless erosion of time. The endless, rhythmic pounding of these water-powered hammers was the sound of a civilization thinking on a truly epic scale. It allowed for projects of a scope that would have been logistically impossible with manual labor alone. The sheer volume of processed material needed for the Great Wall, stretching thousands of miles across every imaginable terrain, demanded this kind of consistent, awesome power. This mechanization reveals a sophisticated understanding of engineering principles that would not become common in the West for more than 1,000 years. It forces us to reconsider the ancient world not as a time of simple hand tools, but as an era capable of grand, automated processes. If a river could be put to work breaking stone, what other natural forces did ancient engineers learn to command, and what tools did they use to manage the colossal human effort these projects required? Those rhythmic trip hammers represent a fundamental truth that large-scale construction is as much about logistics as it is about lifting stone. This leads us to one of history's most unassuming yet revolutionary tools, the Mesopotamian cuneiform tablet. We often picture ancient builders with chisels and ropes, but the most powerful tool in their arsenal may have been a simple slab of wet clay and a stylus. Babylonian architects used these tablets not for poetry or law, but as the world's first blueprints and project management software. With precise cuneiform script, they outlined detailed plans for towering ziggurats and sprawling palaces, calculating the exact number of bricks required, the amount of bitumen needed for mortar, and the size of the workforce for each phase of construction. This was administrative genius etched in mud, the mythological story of the Tower of Babel, a project doomed by a failure of communication, finds its grounding reality in these very tablets. They were the antidote to chaos, the instruments that coordinated thousands of workers, many speaking different languages, toward a single, monumental goal. By having a clear, permanent, and distributable plan, project managers could ensure that every team, from the brickmakers by the river to the bricklayers on the summit, was working in perfect synchrony. The survival of structures like the ziggurat of Ur for over 4,000 years is not just a testament to the quality of the bricks, but to the quality of the organization behind them. Flawless execution requires flawless planning, and these clay tablets provided the master plan that prevented costly errors and ensured structural integrity from the ground up. This administrative technology forces us to look past the physical grandeur of a landmark and appreciate the invisible architecture of information that made it possible. And if a clay tablet could ensure the stability of a ziggurat, it makes you wonder what other tools were used to guarantee the stability of the very ground beneath it, the critical foundation that remains unseen. That invisible architecture of information required an equally precise mastery of the physical world, starting at the very ground level. The legendary straightness of a Roman road or the impossibly gentle slope of an aqueduct did not begin with the stone, but with water itself. Roman engineers deployed a tool of profound simplicity, a temporary network of wooden gutters used in concert with the ever-faithful plumb bob. Before any foundation trench was dug, workers would lay out these shallow channels across the landscape, following the intended path of their structure. Then they would carefully pour water into the system. The fundamental principle of hydraulics took over, as water always finds its own level. By observing the water's surface at various points along the gutter, engineers could mark a continuous line of identical elevation across hills and valleys. This established the all-important gradient. At each marked point, the plumb bob would then come into play, transferring that level mark vertically down to the ground to stake out the exact depth for the foundation piers. This combination of water's horizontal truth and the plumb bob's vertical truth created a three-dimensional grid of absolute precision. The mythology of Roman infrastructure is encapsulated in the Pont du Gard aqueduct in France. This colossal three-tiered bridge carries a water channel that descends a mere 17 meters over a distance of 50 kilometers, a gradient so slight it seems to defy physics. This was not magic, it was the direct result of the gutter and plumb bob method, applied with relentless consistency. The endurance of these structures for 2,000 years rests on this foundational accuracy. A single uneven pier would have created turbulence and stress, dooming the aqueduct to a rapid collapse. Instead, the water flows as smoothly today as it did for the Romans, a silent tribute to an empirical genius that understood the power of natural laws. This obsession with perfect alignment did not end with the foundation. It extended to the very joints that held the stones together. The stability of those perfect joints relied on a principle that seems to defy logic, an architecture of balance built without a single arch. The Mycenaean corbelled arch template was a tool of pure geometry, a temporary wooden framework that guided the placement of colossal stones in a breathtakingly slow inward crawl. Unlike a true Roman arch that uses a keystone to lock everything into compression, a corbelled arch is built by laying each stone so that it projects slightly farther inward than the one below it. This creates a cantilever effect, with each block's weight counterbalancing the one opposite it. The wooden template was the master plan, a physical guide that ensured every stone was set at the exact angle needed for this delicate equilibrium. The result is the iconic Lion Gate at Mycenaean, a massive opening topped with a triangular slab carved with lions, all supported by a vault of stones that appears to hang in mid-air. This technique is the very source of the term Cyclopean masonry, the ancient belief that only giants, the mythical Cyclopes, could have lifted and fitted such enormous boulders. The mythology was born from the sheer improbability of the structure, but the real magic was not superhuman strength. It was the invisible wooden guide that provided the certainty of mathematics. The template was a tool of foresight, allowing builders to see the finished arch before the first stone was laid, ensuring that the final, closing stone would fit perfectly. This method created structures of immense durability, as the constant gravitational pressure only makes them stronger over time. The fact that the Lion Gate has stood for over 3,000 years, surviving earthquakes and wars, is a testament to the enduring power of this simple, brilliant principle. The tool itself, the wooden template, has long since rotted away, leaving behind only the stone puzzle it helped solve, a puzzle that continues to stand as if held up by myth itself. This achievement makes the method for lifting those multi-ton stones into their precarious positions all the more incredible to consider. The same principles of balance that stabilized a corbelled arch were tested on the open ocean, where a single misjudgment meant vanishing without a trace. The Viking Sunstone stands apart from our other tools, not for shaping stone, but for navigating the featureless sea. This was not a map or a compass, but a crystal of Iceland spar, a form of calcite with a unique property. On a cloudy day, when the sun was completely hidden, a skilled navigator could hold this translucent stone to the sky and slowly rotate it. By looking through the crystal, they could detect subtle patterns in the polarization of daylight, a hidden signature of the sun's position invisible to the naked eye. This allowed them to pinpoint the sun's location with remarkable accuracy, even through thick fog or cloud cover. With this single reference point, they could establish a reliable line of longitude, a fixed east-west bearing across the trackless Atlantic. The legendary voyages to Iceland, Greenland, and the coast of North America were not just acts of blind courage. They were feats of sophisticated celestial navigation made possible by this ingenious device. The mythology of the Viking longships appearing as if from nowhere on distant shores is grounded in the quiet science of the Sunstone. It was this tool that enabled the transport of people, resources, and, most importantly, knowledge. The very timber frames of their settlements in new lands, the building techniques they carried across the sea, all depended on the ability to complete the voyage. This reminds us that the most crucial tool for construction can sometimes be the one that enables the journey itself, the instrument that allows ideas to cross oceans and take root in new soil. How many other foundational technologies were born from the need to simply arrive at a place where building could even begin? The Viking Sunstone guided ships across the trackless sea, but another civilization used a different kind of tool to guide the land itself toward abundance. The Aboriginal Australian fire stick is perhaps the most profound tool on our list, one that built not with stone but with life. This was not a complex instrument, simply a long, smoldering stick carried by generations of Indigenous Australians. Its purpose was fire stick farming, a practice of controlled, low-intensity burning that sculpted the continent for tens of thousands of years. These carefully timed burns were not destructive wildfires, they were a form of ecological gardening. They cleared away dense, dry undergrowth, preventing the catastrophic blazes that can devastate a landscape. More importantly, the ash left behind enriched the soil, triggering the germination of new plants and attracting kangaroos and other game animals for hunting. The mythology of the Dreamtime is not just stories etched in the stars. It is coded into this very practice, a spiritual understanding that people are active custodians of the land, not passive inhabitants. The open, park-like forests and sweeping grasslands that the first European settlers marveled at were not a pristine wilderness. They were a curated landscape, a living landmark meticulously maintained by the strategic application of fire. This challenges our entire definition of what a landmark truly is. Is it only the inert stone of a pyramid or a cathedral? Or can it be a thriving, sustainable ecosystem actively shaped by human wisdom? The endurance of this practice for over 50,000 years stands as a testament to a form of engineering that works in harmony with nature rather than conquering it. The fire stick forces us to expand our vision and recognize that the most enduring structures may not be made of stone at all, but of the very balance of life itself. This leads us to consider the ultimate organic building material, one that grows around you as you build. That living landscape shaped by fire finds its parallel on the open ocean, where a different kind of knowledge built entire civilizations. The Polynesian star compass required no physical instrument at all, just a mind trained to see the sky as a perfect, rotating map. This was a mental model of incredible complexity, memorized by master navigators from childhood. They knew the exact point on the horizon where each of hundreds of stars would rise and set. As one star climbed too high to be useful, another would take its place on the same bearing, creating a celestial highway across the night. But their navigation did not stop with the stars. They read the ocean itself, interpreting the patterns of swell rebounding off distant islands, the flight paths of birds at dusk, and the subtle colors in the clouds that hinted at land beyond the horizon. The mythology of the demigod Maui fishing islands from the sea is a poetic reflection of this reality. With nothing but this knowledge, voyagers in double-hulled canoes discovered and settled every habitable island across the Pacific, an area larger than all the continents combined. The very existence of landmarks like the Maori Pa, the fortified earthwork villages of New Zealand, is a direct result of this voyage. These structures, built on high ground for defense, represent the end point of the longest migration in human history. Similarly, the isolation that allowed the unique culture of Rapa Nui to flourish and carve its iconic moai statues was a product of this navigational art. The star compass itself left no archaeological trace, yet it was the most vital tool of all, the key that unlocked the door to new worlds. This mental technology stands in stark contrast to the brutal physicality required next, the tools that would actually shape the stone giants that now stand as silent sentinels on remote shores. The volcanic tuff of Rono-Raraku Quarry is soft enough to be carved, yet hard enough to endure for centuries, a perfect canvas for the Rapa Nui Toki. This was not a complex machine, but a handheld adze, a basalt stone carefully shaped and lashed with cordage to a wooden handle. With this simple tool, generations of carvers patiently shaped the island's soul. The process was one of relentless repetition, a rhythmic chipping away at the rock face. A team would work on a single moai, using the dense basalt toki to pound and shear away the softer volcanic tuff, defining the stern brow, the long nose, and the prominent chin that stare out across the island. The mythology that the moai walked to their coastal platforms is a beautiful allegory for the truth, which was an effort of unimaginable human strain. The creation of nearly 1,000 statues, some towering over 30 feet tall and weighing more than 80 tons, using little more than stone pounding on stone, represents a pinnacle of pure persistence. The Toki itself is a testament to a profound understanding of materials. The carvers chose a stone harder than their canvas, applying a technology so fundamental it seems almost elemental. While the mystery of their transportation rightly captures our imagination, the greater marvel may be the creation itself. This achievement forces a humbling question: if they could carve giants with such basic tools, what brilliant yet simple method did they devise to move them? The rhythmic pounding of the Toki gave the moe its form, but it was the rhythmic rocking of a simple sledge that may have given it life. The hypothetical moe moving sledge is a tool born of pure physics, not complex machinery. Think of a strong, reinforced wooden platform, a sled resting on a path of lubricated soil or mashed sweet potatoes to reduce friction. Teams of workers would have used ropes not to simply pull, but to create a pendulum-like motion. They would pull one side of the statue upward and forward, then release it, allowing the massive stone figure to rock onto its opposite corner. This was not a steady drag, but a controlled side-to-side walking motion. With each coordinated heave on the ropes, the multi-ton statue would inch forward, seemingly ambling across the landscape under its own power. Modern experiments have proven this method's shocking efficiency. A replica moe weighing many tons can be moved several hundred feet in an hour by just a dozen people using this technique. The local legend that the statues walk to their ahu platforms is not a flight of fancy. It is a perfect folk memory of the visual spectacle this method would have created. The statue would have appeared to sway and shuffle toward the coast, a giant animated by human collaboration. This tool's genius lies in its understanding of momentum and center of gravity. The workers were not fighting the statue's immense weight. They were coaxing it into motion, using its own mass to assist in the journey. It transforms the story from one of impossible burden to one of clever, applied physics. The sledge itself, likely made of the island's now vanished palm trees, would have been a temporary device, reused until it broke and then recycled, leaving no trace for archaeologists to find. This controlled rocking principle connects to a global pattern of ancient ingenuity, where the challenge of moving the immovable was often solved by making the object dance, not drag. The silent, swaying journey of the moe was a triumph of oral tradition and coordinated effort. But for a project as vast and precise as the Great Pyramid, memory alone would never suffice. The true blueprint for eternity was written not in stone but on papyrus. The Egyptian papyrus roll was the ancient world's equivalent of a master architect's hard drive, a fragile yet enduring repository of sacred engineering knowledge. Imagine a scroll not filled with poetry or history, but with meticulously drawn geometric diagrams, calculations for ramp angles, and precise lists of materials required for each ascending course of a pyramid. These were the working documents of the master builder, the detailed manuals that translated a pharaoh's divine command into 1,000,000 tons of perfectly placed limestone. The mythology of Imhotep, the genius architect who designed the first pyramid for Pharaoh Djoser, is inseparable from this concept. He was later deified not merely as a builder, but as a sage who codified the art of construction, turning it from a crude craft into a sacred science. The papyrus roll was the physical manifestation of this codification. It would have contained the religious formulas for aligning a temple to the rising sun of the equinox, ensuring its connection to the cosmic order. It detailed the step-by-step sequences for constructing a corbelled vault or setting the cornerstone of a massive pylon gate. This was knowledge preserved and transmitted with exacting precision from one generation of builders to the next. The survival of these structures for over 4,500 years through earthquakes and shifting sands is the ultimate testament to the accuracy locked within those fragile scrolls. A single error in the calculations for the pyramid's base, a mistake in the slope angle, would have caused the entire structure to buckle under its own weight. The fact that it still stands is proof that the knowledge on the papyrus was flawless. This intellectual tool forces a profound realization. The greatest construction tool was not the copper chisel or the limestone ramp, but the organized, written knowledge that dictated their every use. It underscores that the most powerful instrument is often the one that orchestrates all the others, the plan that turns chaos into a timeless monument. And if a papyrus scroll could guide the placement of a pyramid's core stones, what incredibly precise instrument was needed for the final, delicate adjustments, for setting the gleaming white casing stones that would reflect the sun like a mirror? That obsession for perfect alignment found its ultimate expression in the management of water itself. The Roman chorobates was a tool of almost philosophical elegance, a long wooden bench, perhaps 20 feet in length, supported by 4 sturdy legs. Along its top ran a shallow, precisely carved channel. An engineer would fill this groove with water and then patiently wait for the liquid to become perfectly still, its surface a flawless plane mirroring the horizon. To confirm this delicate equilibrium, they used plumb lines hanging from each end of the bench, ensuring the entire structure was not tilted. Once the water was calm, its surface became the absolute reference point. By measuring the distance from this water line to the ground at various points along the intended path of an aqueduct, the engineers could map out a gradient of unbelievable consistency over many miles. This was a level of precision far beyond what a simple frame level could achieve over such vast distances. The mythology of Roman civilization, its promise of order and cleanliness flowing into chaotic territories, was made real by this instrument. The aqueducts it helped build, like the magnificent Pont du Gard, are marvels not just of scale but of subtlety. Their channels descend at a gradient of sometimes just 1 foot per mile, a slope so gentle it seems impossible to the naked eye. Yet this exactness was essential. A slope too steep would cause the water to flow with destructive force, eroding the channel walls. A slope too shallow would allow the water to stagnate. The chorobates provided the geometric truth that prevented both failures. The fact that some Roman aqueducts remained in continuous use for over 1,000 years, and a few even function today, is a direct tribute to the unwavering accuracy of this long wooden bench. It was a tool that translated the abstract principle of a level line into a physical reality of flowing water, the very lifeblood of an empire. And once that perfect course was established, another tool was needed to carve the stone channels that would carry that lifeblood with minimal loss or turbulence. The seamless walls of a Gothic cathedral were not born smooth, but were earned through a final, grinding ritual. After the treadwheel crane had lifted each massive block into its precarious position, the medieval mason's drag went to work. This tool was deceptively simple, a flat iron plate studded with sharp, hardened teeth, its handle worn smooth by generations of calloused hands. A worker would pull this abrasive rake back and forth across the stone's surface, the sharp points biting into the high spots, grinding them down to meet the low. It was a process of brutal patience, turning a rough-hewn block into a geometrically perfect piece of an immense puzzle. This was not merely about aesthetics, it was a matter of structural survival. A single uneven surface would create a point of concentrated stress, a weakness where water could seep in, freeze, and expand, slowly but surely prizing the masonry apart over the centuries. The drag ensured that the weight of the vaulted roof was distributed evenly across every square inch of contact between stones, a perfect transfer of force that is the true secret to the cathedral's endurance. The mythology here is tangible, the belief that a house of God must be as flawless as human hands can make it. The rhythmic scraping of the drag was a physical prayer, an act of devotion that prepared each stone to bear its share of a divine burden for 1,000 years. This obsessive focus on the surface, however, was merely the canvas. The true artistry, the language of faith itself, was yet to be carved into it. The smooth, prayerful scrape of the drag created a perfect surface, but the stones themselves were still bound by the rigid logic of right angles. To truly capture the heavens, architecture needed to break free from the box. The Byzantine pendentive template was the key to this celestial escape. This was not a simple tool for measuring or cutting, but a complex three-dimensional wooden framework that defined a new form of architectural space. Its purpose was to solve an ancient geometric puzzle: how to place a vast circular dome seamlessly atop a square building. The answer was the pendentive, a curved, triangular segment of a sphere that acts as a graceful transition, filling the corner gaps between the square base and the circular drum of the dome. The wooden template was the physical guide that allowed masons to lay each brick and each trowel of mortar along the exact, perfect curve required. Without this guide, the delicate balance of forces would have been impossible to achieve. The result was the revolutionary dome of the Hagia Sophia, a structure that seemed to float on a ring of light pouring in from its windows. The mythology of the dome as the vault of heaven was not just a symbolic idea, it was an engineering reality made possible by the pendentive. This innovation distributed the immense weight of the dome down into the four massive piers at the corners of the square, rather than outward, allowing for a dome of unprecedented size and apparent weightlessness. The survival of the Hagia Sophia for nearly 1,500 years, through countless earthquakes that have toppled lesser structures, is a direct tribute to the enduring strength of this brilliant solution. The wooden template itself has long since turned to dust, but the perfect curvature it instilled into the brick and mortar remains, a frozen moment of architectural genius that transformed the very ambition of building. This mastery over rigid stone to create fluid forms naturally leads to a different kind of challenge: the tools needed to work with materials that are strong, yet inherently flexible. The transition from rigid stone to flexible bark marks a different kind of architectural genius. While cathedrals reached for the sky, another civilization mastered the art of moving across the earth to build their own lasting landmarks. The Native American birch bark canoe was far more than a means of travel. It was the essential construction vehicle that made entire villages possible. Its design was a marvel of lightweight strength. A frame of pliable white cedar ribs was sheathed in large, carefully stitched panels of waterproof birch bark, all sealed with a gum made from spruce resin. This vessel could carry astonishing loads, yet was so light that a single person could portage it around rapids. This was the key to unlocking a continent. Along the vast river systems of North America, the canoe became the logistical backbone for building. It transported the tools, the materials, and the people themselves to strategic sites. Heavy stone axes for felling giant trees, bundles of saplings for weaving the walls of longhouses, and rolls of bark for roofing could all be moved efficiently to a chosen location. The establishment of fortified villages with their protective palisades and large communal dwellings was a direct result of this mobility. The mythology of the canoe in many nations often portrays it as a spiritual vessel, a guide for the soul. This spiritual connection is deeply rooted in its physical role as the literal vehicle that carried the community toward a new home. enabling the gathering of disparate resources into a single, fortified whole. The great longhouses of the Iroquois, some over 300 feet long, could never have been supplied by land alone. Their construction required the silent, steady traffic of canoes, a logistics network that moved timber from upstream and stone tools from distant quarries. This tool forces us to remember that the most critical phase of any great project is often invisible in the final structure, the monumental effort of simply bringing everything together. The canoe ensured that the right materials arrived at the right place, making it the silent, floating prerequisite for every landmark that followed. The legend of Archimedes defending Syracuse presents a tool of terrifying scale. As the Roman fleet closed in on the city walls, a massive wooden crane, known as the Claw of Archimedes, swung out over the water. Its arm lowered a grappling hook into the sea, catching the hull of an approaching warship. Then, through a system of counterweights and pulleys, the machine would heave the vessel partially out of the water. The leverage was so immense that the ship could be shaken violently, even capsized, and then dropped back into the sea to sink. While historians debate its exact existence, the claw was not mere magic. It was a brutal public demonstration of the lever principle that Archimedes himself had defined. "Give me a place to stand, and I shall move the earth," he is said to have claimed. The claw was that philosophy made monstrously real. The same physics that could hoist an enemy galley were the very essence of peaceful construction. The cranes that built the great lighthouse of Alexandria, one of the Seven Wonders, operated on identical principles of leverage and pulley systems. The machinery needed to lift the massive stone blocks for harbors and fortified walls was a direct cousin to this defensive weapon. This duality lies at the heart of ancient engineering, where the tools of creation and the tools of destruction were often one and the same. The genius required to protect a city was the same genius required to build it, a reminder that the most powerful inventions are neutral, their purpose defined only by the hands that wield them. This constant need for protection drove the evolution of tools designed not for lifting, but for locking a city shut against the world. The very walls built to withstand an assault were often best understood by those who knew how to breach them. In the ancient world, the most dramatic lesson in structural engineering was taught by the Mesopotamian siege ramp. This was not a tool for creation, but for controlled demolition, a mountain of earth and timber constructed with the same meticulous care as a temple. Assyrian armies, famous for their terrifying efficiency, did not simply pile dirt against a city's walls. They engineered these ramps with calculated slopes, reinforced with layers of timber and stone for stability, creating a durable roadway capable of supporting the weight of heavy battering rams and assault towers. The process mirrored the construction of a ziggurat in reverse, applying identical principles of material science and load management. The mythology of cities like Babylon, famed for walls that seemed to touch the heavens, is inseparable from the constant threat of these earthworks rising against them. A commander who could build a ramp that would not collapse under the strain of his own war machines possessed a deep, practical understanding of how to build foundations that would never fail. This knowledge was a brutal form of reverse engineering. By learning the precise amount of force and the specific angles required to undermine a wall, an engineer gained invaluable insight into how to construct a wall that could resist those same forces. The experience of building a temporary, destructive monument directly informed the creation of permanent, defensive ones. It reveals a profound truth about ancient ingenuity, where the line between builder and destroyer was often blurred. The same mind that could calculate the slope for a ramp to topple a fortress could also calculate the foundation for a gate that would never fall. This cycle of creation and destruction fueled an endless arms race of architectural innovation, where every new defensive technique was born from understanding the last successful attack. That silent, floating prerequisite of the canoe highlights a universal truth that a great project is only as strong as its weakest logistical link. On the other side of the world, another civilization perfected the art of coordination without ever putting pen to paper. The Inca quipu was a language made of string, a complex recording device that managed an empire spanning thousands of miles of rugged Andes mountains. At first glance, it appeared to be a simple collection of colored cords hanging from a main line, but within those threads lay a sophisticated code. The type of knot, its position on the cord, the color of the string, and even the spin direction of the fibers all held specific meaning. This was not just an abacus for counting. It was a dynamic database for managing the impossible logistics of building sites like Machu Picchu. A quipu could record the number of laborers dispatched from a specific village, the quantity of stone blocks quarried from a particular site, and the amount of food supplies needed to sustain the workforce for a month. A runner or chasqui would carry these knotted messages along the empire's elaborate road system, delivering vital instructions to foremen in remote locations. The mythology of the Inca as master organizers, capable of moving mountains of stone and manpower with divine efficiency, finds its physical form in the quipu. It was the nervous system of the empire, allowing the central government in Cusco to orchestrate the simultaneous construction of terraces, temples, and storehouses across a vast and fractured landscape. The survival of Machu Picchu, perched so perfectly on its ridge, is a testament not just to the stonemason's skill, but to the flawless supply chain that the quipu managed. This abstract tool forces a profound realization that the most vital instrument for a landmark may be the one that never touches a single stone. It was the system that ensured the right people and the right materials arrived at the right time, turning a vision of stone into a city that has defied the clouds for centuries. High above the stone vaults, in a world of smoke and searing heat, the medieval metalworker performed a final act of alchemy. His tool was a heavy iron ladle, swung from a chain over a roaring furnace until it glowed with the weight of molten lead. This was not a task for the faint of heart. One misstep, one splash of the liquid metal, and the consequences were dire. Yet this dangerous ritual was essential for granting the cathedral its true immortality. The wooden roof structures, the intricate trusses that supported the entire edifice, were vulnerable to the very elements they defied, to rain and snow that would rot them from within. The ladle was the answer. Workers would pour the shimmering lead onto specially prepared wooden substrates, creating a continuous, seamless skin that shed water for centuries. The mythology of the cathedral as a shining beacon was quite literal, its lead roof catching the sun like a dull gray mirror, a permanent crown forged in fire. This application of metallurgy was a final, masterful layer of defense, a perfect seal that preserved the complex timber skeleton from decay. The endurance of Westminster Abbey's roof is a direct result of this hot, hazardous work, a testament to the courage and skill of the artisans who literally poured a permanent shield over the prayers below. With the structure now sealed against the sky, the focus could turn inward to the tools that would transform sunlight into the very language of faith. That shimmering lead roof sealed the cathedral against the storms of the world, creating a dark, cavernous space within. And into this sacred darkness, the builders needed to pour a different kind of light, one composed of color and narrative. The breathtaking stained glass of medieval cathedrals was not created by random inspiration. It began with a full-sized drawing, a master plan known as a cartoon. This detailed outline of a saint or a biblical scene was the essential blueprint. But how do you copy such intricate artwork, with its flowing lines and delicate features, onto dozens of separate, uneven pieces of colored glass. The answer was a tool of elegant simplicity, the pounce bag. Imagine a small, porous cloth pouch like a tiny pillow filled with fine charcoal dust or chalk powder. The artist would take the paper cartoon and prick thousands of tiny holes along every single line of the drawing with a sharp stylus, effectively turning the image into a complex stencil. This perforated cartoon was then carefully laid over a clean sheet of glass. The artisan would then gently pat the pounce bag over the entire surface. With each tap, a fine black or white powder would sift through the perforations, leaving a dotted outline of the entire design directly on the glass beneath. This dotted line was the guide, the faithful map that the glass painter would then follow, filling in the details with vitreous paint before the piece was fired in a kiln, fusing the image permanently to the glass. This humble bag was the key to mass-producing sacred art with unwavering accuracy. It allowed for the exact replication of a single majestic design, like the rose window of Notre Dame, across hundreds of individual glass pieces, ensuring that when they were all fitted together with lead came, the final image was seamless and perfectly coherent. The entire mythology of the Gothic cathedral, where light itself was considered the divine presence, was filtered through these brilliantly colored windows. The stories of Scripture were literally translated into luminous paintings that illiterate congregations could understand. The survival of these fragile artworks for over 800 years, through Reformation and Revolution, is a miracle of craftsmanship. But it is also a testament to the pounce bag, the unassuming tool that ensured every angel's wing and every saint's gesture was rendered with a consistency that made the divine stories glow with timeless clarity. While the cathedrals of Europe reached for the heavens, a different kind of architectural marvel plunged deep into the earth. In the arid landscapes of India, the challenge was not to build up, but to dig down to the life-giving water tables hidden far beneath the surface. The ancient stepwell crane and bucket system was the ingenious answer, a tool that inverted the entire logic of construction. This was not a single tool, but a coordinated assembly of wooden cranes, ropes, and large leather buckets, all working in unison to carve out monumental spaces below ground level. Teams of workers would operate these cranes from various landings and steps of the partially excavated well, creating a vertical assembly line. As one team dug deeper, another would use a crane to lift heavy baskets of earth and rock up to the next level where it could be hauled away. Simultaneously, other cranes would lower precisely carved stone blocks, mortar, and tools down into the deepening pit. This constant, orchestrated flow of material moving in both directions turned the construction site into a living, breathing entity. The result was a structure like Rani Kai Vav, a stepwell that descends 7 stories into the ground, adorned with hundreds of intricate sculptures. This was not merely a water source, it was an inverted temple, a sacred space dedicated to water deities where every step downward was a spiritual journey. The crane and bucket system made this mythological concept a physical reality, allowing builders to work with the same precision and artistry underground as they could under the open sky. It represents a complete mastery of the vertical dimension, proving that the most profound landmarks are not always those that scrape the clouds, but sometimes those that honor the depths from which life itself springs. The graceful curves of a pagoda's roof are a deliberate deception, an architectural lie that conceals its true purpose. High above the decorative tiles lies the real genius of Chinese construction, the Du-Gong bracket system. This was not a rigid framework of nails and bolts, but a complex 3-dimensional puzzle made entirely of interlocking wooden pieces. Each bracket or du and each arm or gong was carved to fit together with its neighbors in a way that seems almost organic. The tool that made this possible was a master template, a set of precise wooden patterns that guided the hands of countless artisans. These templates ensured that every single bracket, produced by different craftsmen in different workshops over many years, would snap together with absolute perfection without a single metal fastener. The result is a structure with a hidden secret: flexibility. When an earthquake strikes, a rigid stone tower is vulnerable, its walls cracking under the seismic shock. But a pagoda built with dugong brackets behaves differently. The entire wooden frame is designed to sway as a single, unified entity. The interlocking joints absorb and dissipate the energy of the tremor, rocking gently like a tree in the wind rather than shattering like a block of ice. The mythology of harmony between heaven and earth is not just a spiritual idea here, it is an engineering principle. The Forbidden City in Beijing has survived hundreds of earthquakes over 6 centuries precisely because of this system. Its grand halls are not anchored rigidly to the ground, but are instead seated upon a flexible wooden skeleton that dances with the Earth's movements. This is the pinnacle of organic engineering, a profound understanding that true strength is not found in unbending resistance, but in the ability to yield, to absorb, and to endure. From the simple plumb bob to the mental map of the stars, these 30 forgotten tools reveal a universal truth: that humanity's greatest landmarks were built not by magic, but by a profound and patient ingenuity. Each instrument, whether carved from wood or born from a deep observation of nature, represents a moment of brilliant problem-solving. The real protagonists in the mythology of our ancient wonders are not the pharaohs or emperors who commissioned them, but the countless unnamed hands that mastered these devices. They understood the world in a way we have nearly forgotten, turning the raw forces of gravity and water into allies for creation. Their legacy is a foundation of practical skill, a reminder that the most enduring structures rise from a deep respect for the materials and the laws of physics. The next time you stand before a monument that seems to defy time and logic, remember the forgotten tools, the quiet genius that made the impossible stone by perfect stone. If this journey into the past has sparked your curiosity, we would love to hear which of these tools amazed you the most in the comments below. For more explorations into the hidden histories that shape our world, be sure to subscribe.